Hello, everyone. This is Randall Pike. Today's lecture is on diagonalization of symmetric matrices. This is a continuation of a section we did previously when we talked about diagonalizing matrices. We're specializing to the case of symmetric matrices. So remember, a symmetric matrix is one whose transpose is equal to itself. All right, and we'll see some examples down below. So that's the matrix, the type of matrix we're going to be discussing in this entire lecture. Some facts that we may or may not establish in detail are the following: that symmetric matrices have real eigenvalues. Remember that a matrix generally has real and complex eigenvalues, and that's because roots of polynomials with real coefficients will have real or complex roots. For symmetric matrices, the case is only real eigenvalues, and this we proved in the case of 2x2 matrices. Okay, we wrote out the formula for we found the characteristic polynomial 2x2 matrices, and we showed that the roots of that quadratic are real when the matrix is symmetric. So 2x2 matrices. Okay, but it holds for all n by n matrices. Just a more complicated proof. Symmetric matrices are always diagonalizable. And what this means is, as we've seen previously, diagonalization means that the matrix has n linearly independent eigenvectors. So what this means is that symmetric matrices have n linearly independent eigenvectors. If you recall, the criteria for a matrix to be diagonalizable was exactly this: it must have n linearly independent eigenvectors. Okay, symmetric matrices always have n linearly independent eigenvectors. And what's more, for symmetric matrices, so let me write up here. First, recall, for any matrix, any square. So whenever we're talking about eigenvalues and eigenvectors, the matrix is always square. So for any square matrix, this is a fact to recall. For any square matrix, eigenvectors corresponding to different eigenvalues are linearly independent. Now that we didn't prove that, it's a little bit it's a little bit long, but it's tangible, and I think that's a remarkable fact. Dependent. Okay, so they're linearly independent automatically. Let me just finish this up, then I'll come back to symmetric matrices. So what this means, so that is, okay, if V1 to Vk are eigenvectors, of A, so A is just a square matrix that we're discussing. So if we have k eigenvectors of A corresponding to different eigenvalues, so let me write it out. So A Vi equals lambda I Vi, and the lambdas are distinct. Okay, so they're all different. Okay. Then this set, V1, Vk, is a linearly independent set of vectors. Okay, so that's what we mean by eigenvectors associated to different eigenvalues are linearly independent. So continuing on with this, this same discussion about an arbitrary matrix and its eigenvectors. So if script I is a basis for eigenspace EI of A, and let's say there's k of them, so k eigenspaces, then if I take the union of all these vectors, V1 union, so these are bases of the corresponding eigenspaces. I take the union of all those vectors. This set beta script B is linearly independent. Okay, so you can create a large set of linearly independent vectors by taking the union of all the bases. In the case where this matrix A is diagonalizable, then B is a basis for Rn. So in the case A is diagonalizable, then this B is a basis for Rn, which means that you have n vectors in it. So in the union of B1 to Bk is n vectors. Okay. Now these bases Bi you find for the eigenspaces, those ones we've done many times in this course. You know, these sets of vectors via solve, you know, this matrix. So lambda I minus B x equals 0. Solve that system. What you get when you write out the solution set is something like this. So T1 W1 plus dot dot T, let's say P WP. When you row reduce that matrix to find the eigenvectors, you read off the solution this way, and it's these vectors W1 to WP which form your bases. So BI is this set. So that's how you identify the eigenvectors. And these W1 to WP will be linearly independent because that, due to the fact that the row reduction, when you row reduce this matrix, the coefficient matrix, this one here, when you row reduce that and then you read off the solution this way, those vectors W1, WP are linearly independent. Okay, so this is how you did obtain your bases for the eigenspaces. And if you were diagonalizing the matrix A, then you'd string together these bases for each eigenspace, and you'd be assured that the complete string, which would be this script B here, would be linearly independent, and hence it would be a basis for Rn. Okay, so that was the situation for arbitrary square matrix. Whether or not it's diagonalizable, eigenvectors corresponding to different eigenspaces will be linearly independent, okay? And if it is diagonalizable, it just means that there's enough eigenvectors to form a basis. Now, let's go back to this statement up here. The symmetric matrices have not only linearly independent eigenvectors, but orthogonal eigenvectors. So the eigenvectors from different eigenspaces are orthogonal. Okay, so let's do this here now. But if A is symmetric, so that's an additional criteria on this matrix A. In fact, eigenvectors from different eigenspaces are orthogonal. Okay, so in other words, if A vi equals lambda I vi and A vj equals lambda j vj, where lambda I is distinct from lambda j, then vi dot vj will be 0. Okay, so so now if you take, so generally, so let's write it out this way. If so you pick up vi in this eigenspace here, or actually let's write it that way. You form a basis, and vj from the basis for the eigenspace ej, then vi dot vj will be 0. The question is, can we form an orthogonal basis from, so an orthogonal basis for Rn from the BI, okay? So it's true because a symmetric matrix is diagonalizable. The eigenvectors, if you put all those bases for each eigenspace together, that's a basis for Rn. And it's true that different eigenvectors from different bases will be orthogonal, but it's not true, right, that going back to this here now in orange, when you find the vectors in the base for a basis of the eigenspace this way, even in the case of symmetric matrices, these W1, WP do not have to be orthogonal amongst themselves. They don't have to be, and they typically won't be. When you extract these W1s to WP from your row-reduced echelon form of this coefficient matrix, there's no reason why they should be orthogonal. So what you'd have to do there is you'd have to apply the Gram-Schmidt method to make them orthogonal, and then you'd get an orthogonal basis. So I'll mention this again below at the end, but let me just say it here. Can we form an orthogonal basis for? Yes, yes, but need to apply Gram-Schmidt method to each basis bi to obtain orthogonal or orthonormal. So if you normalize them, they'll be orthonormal. Okay, to obtain orthogonal or orthonormal bases for each eigenspace. Okay, then once that's done, you can string together all those bases to get an orthogonal or an orthonormal basis for Rm. So there's a little bit more work to do when you want to orthogonally diagonalize a matrix A than if it's not symmetric and you just want a basis of eigenvectors. So here we want a basis of an orthogonal basis of eigenvectors. So that's the content of this last fact here. Symmetric matrices have orthogonal eigenvectors. I mean, the consequence of that is that we will be able to build an orthogonal basis or an orthonormal basis of its eigenvectors, using its eigenvectors. Okay, so back to symmetric matrices, just to remind you, so these are matrices that are equal to their transpose. Okay, so some examples here. So remember, when you take here's a 2x2 example. When you take the transpose of a matrix, the diagonal entries stay the same. So there's the two entries along the diagonal of this 2x2 matrix. So if I put a number up here, then when I take the transpose, this entry has to be the same as this entry down here. Okay, so in other words, in terms of entries, the ijth entry of aij, is the ijth entry of at. Okay, that's what that equation says. But the ijth entry of at is the ji entry of a. So that's the consequence of a matrix being equal to its transpose, is that the ijth entry of A must be the same as the jith entry of A. So that's what I'm trying to do here when I write my matrices. When I wrote down this 2 to begin with, I knew that that's the 1, 2 entry. Therefore, the 2, 1 entry must also be this number, and the 2, 1 entry was this one here. Okay, so we can see that if I draw a line through the diagonal, the entries reflected across the diagonal, and there's only 2 in this case, are the same. So we reflect across the diagonal. So it's very easy to identify symmetric matrices. If I do a 3 by 3 case here, so let me put my diagonal entries first. Okay. Now, when I start to put in entries on the other spaces, the other spots here, if I put a 0 there, then its reflection, let me draw the diagonal line, so think of that as the mirror, the reflected image of that must be the same number, so that's over here. So if I put a 2 down here, the reflection of that 2 is the upper corner here, so I must put a 2 up there. Okay, so I'm having so far so good. And then whatever number I put here, when I reflect that across the diagonal, it appears down here. Okay, so that's a 3 by 3 symmetric matrix. Okay, so very easy to identify symmetric matrices, very special form. And because of this special form, these many important consequences come out of that. They have real eigenvalues. I can always diagonalize them. And even more, I can always orthogonally diagonalize them. Okay, which means that their eigenvectors are orthogonal. So there's a lot of consequences from this symmetry that they have, that they're equal to their transpose. That being said, you may think that these are very special. We might not see them very often. They're very special kind of symmetry. However, these kind of matrices appear quite frequently in applications of linear algebra, so it is very important for us to study them, and that's what we're doing in this section here. Okay, so let's go back to a previous section, 6.2. So diagonalizing a matrix. So we're going to follow that algorithm in 6.2. Let me just remind you here again. Diagonalizing a matrix. A matrix A is diagonalizable. If there is an invertible matrix. P such that P inverse A P equals D, and D is diagonal. So that's diagonalizable. Recall this is related to similarity. So recall B and C are similar if B equals M C M inverse. Now, the fact that I wrote M and M inverse means that this matrix M is invertible. Now, I'm just highlighting the difference between the notion of similarity, the slight difference, and what we're talking about diagonalizable, which is a particular kind of similarity. All we mean by B and C being similar is that there is an invertible matrix that I can write this expression here either way. Okay, so it doesn't matter where you put the inverse part of it. That's what I'm saying here. So on the left. Okay, but when going back to the right here, our formula, this is what we mean by diagonalizable. A is diagonalizable, so D is the diagonal matrix. It is important that you put the P inverse there on the left of A, okay, and the P on the right. It is important because, so you have to remember for diagonalizable matrix, you have to remember that the inverse of this matrix P is on the left of A. And one way to remember that is to just rewrite this. So multiply it by P on the right here, both sides, you'll get AP equals PD. Okay, so that follows from the way I wrote the similarity here between A and D. P inverse AP equals D. So multiply both sides on the left by P, you get that. And recall that P is the matrix, right? This was our algorithm, which I'm going to demonstrate in this example. P is the matrix whose columns are eigenvectors of A, right? So P is equal to this matrix. There's the first eigenvector as the first column. There's the second eigenvector. These are ordered in terms of the eigenvalues, say. Okay, so that's what the P is, and this is what the D is. D is the eigenvalues ordered this way along the diagonal entry, so everything else is 0. Now, this is slightly different, the similarity we write for a diagonalizable matrix than the general notion of similar matrices over here, because here we have already identified the P that we need. It's this one down here that has columns that are eigenvectors. And this formula, P inverse AP equals E, will only work if you write it that way. It won't work if you write it PA, P inverse D, for instance. And the way you can see why this is the right way to do it is because when you write it this way, so just multiply on the left by P inverse, then you can see that, so we see that AP, okay, so P is that matrix with column of eigenvectors. So remember, matrix multiplication A times P is the same as A times each column of P. Well, each column of P is an eigenvector, so that would be lambda 1 V1. That would be my first column, right, of AP. My second column would be lambda 2 V2, okay, and etc. So my last column would be this lambda n Vn. Okay, so that's easy to see. And it's also easy to see that that's the same for PD. And that the reason for that is because D is so simple. D is just that diagonal matrix. So do it in your head. Multiply this P, whose columns are the eigenvectors, V1 to Vn. Do that matrix multiplication against this diagonal entry. There's mostly zeros, and only the lambdas on the diagonal. You will also get this answer. Okay, so this is one way you can remember where is the inverse part, the inverse matrix that is used to determine the similarity between A and D. It's on the left, okay, and it has to be on the left because the P is this matrix of eigenvectors. Okay, I just wanted to point that out because you will see discussions of similarity, and you'll see both of these formulas here, and it doesn't matter which one you use because your M and your Q are not specified to be certain matrices. But in the case of diagonalizing a matrix, it is a specific P we're seeking. Okay, and so I've just through this little discussion, I've reminded you how we diagonalize a matrix. We first find the eigenvalues, and then we find the eigenvectors, and if there's n linearly independent eigenvectors, I form the P this way, columns of eigenvectors, and I create this diagonal matrix D with the eigenvalues lined up ordered in the same way as the eigenvectors are ordered in P, and then that equation, P inverse AP, will in fact equal D. So that was what we did in the previous section. So let me show you how it works in, again, I'm going to take a symmetric matrix because that's our topic of discussion. And when we get to the point where we have the eigenvectors, then we can sit back and observe that, in fact, different eigenvectors from corresponding to different eigenvalues are indeed orthogonal. All right, so let's take a not too complicated one here. We'll do a 3x3 one later on. Okay, so let's do this one. Okay, there's a nice symmetric matrix. So I want to diagonalize this matrix, which means I want to find this matrix P so that A is similar to a diagonal matrix, the diagonal entries being its eigenvalues. So we first find the eigenvalues, which means I form the determinant of this matrix now. Okay, and let me put just underneath just once, because in the textbook they do it, they tend to write it the other way. So, or determinant of A minus lambda I. Okay, all right, so it doesn't matter which one you prefer, you use, you'll still get the same eigenvalues. So let's go. So writing it out here, lambda I minus A gives me lambda minus 1, 3, 3 lambda minus 1. So there's my matrix, lambda I minus A. I compute the determinant. It's just a 2 by 2 determinant. So let's just write it out. Lambda 1 squared minus 9, which we simplify as lambda squared minus 2 lambda minus 8. And so we need to factor that. I'll do one more line to find, I need the roots of this one, and this one factors pretty easily. Doesn't have to. I can always use the quadratic formula, but there it is. And so the eigenvalues being the roots. So let's call lambda 1 the eigenvalue minus 2, and let's call lambda 2 the eigenvalue 4. Okay, so there they are. So now we need to find eigenvectors. Okay, so we set up the homogeneous system. So I'm going to choose the first eigenvalue, so minus 2i minus a. So I want to solve this system, remember? Okay, so this gives me the eigenvectors. Now it's a homogeneous system, so we just have to row reduce the coefficient matrix. So in this case, it's going to be, so minus 2 times I minus, so I'm just going to, in this formula right here, okay, this form here, I'm just going to plug in these eigenvalues and form the matrix. So minus 2 minus 1 gives me minus 3, and the other entries off the diagonal are the same, and also it looks like minus 3 here. Okay, so that's the coefficient matrix of that homogeneous system, which is whose solutions are the eigenvectors for that eigenvalue. So I'm not writing the right hand side, you don't need to. So let's row reduce this. Okay, so that's easy to row reduce. I'll just make the top left corner my leading one, and the bottom row will be 0. And so I read off the equation for one of my eigenvectors. Maybe I'll do it the same as I was writing up top there, right? So this is my free parameter, the second variable. So let me call it x1 is t. X2 is my free parameter, okay? So this is my x1 variable, my x2. X2 is my free variable, so it's parameterized by t. And then from this, I extract my vector form of the solution, which is just t times this vector 1, 1. And this is how I identified my vectors that form a basis of the solution space. There's only one in this case, so that's my v1. And then when I go to the next eigenvector, it's 4, so it's 4i minus a. Okay, so I just need that matrix, so let's write it out. So 4 minus 1 is 3, 3, 3, and then 4 minus 1 again is 3. So it's this matrix, that's the coefficient matrix of this system. And I'll row reduce that to 1, 1, 0, 0. Okay, and then we'll see that v2 now is going to be minus 1, 1. Okay, now I can take any multiple of the eigenvector. Okay, it's still an eigenvector, so I selected this multiple. So now I have the two eigenvectors. So now we can we can observe, where'd that go? Yes, in black maybe, observe, okay, that V1 dot V2 is indeed 0. So they're orthogonal, okay? Not only, well, I mean, it's trivial that they're linearly independent, but they're orthogonal. Remember, orthogonality is stronger than linear independence. Okay, so that's our observation of the fact above, that eigenvectors corresponding to different eigenvalues, that's way up here now. This third fact here, eigenvectors corresponding to different eigenvalues are in fact orthogonal. Okay, so let's continue on with our diagonalization algorithm. So now we form that matrix P, and now we form it using the eigenvectors. So the P will be this matrix with, let me put V1 in the first column and V2 in the second column. All right, now I'll need the inverse of P, and it's easy to see that it's given by this matrix right here. So I'll just factor out the 1/2 that appears in all the entries. Okay, so there's my P constructed from the eigenvectors. There they are. There's the V1, there's the V2, and there's the inverse. And then we want to form this product, P minus 1. Let's just check that indeed it does give us the result. So I know that the D will be, because I ordered my columns in P1 by V1 was the first column. So the eigenvalue associated to V1, remember, was a -2. So that's why I put a -2 in the top. And the second entry along the diagonal of D corresponds to the eigenvalue for the eigenvector in the second column of P, which is V2, and that was associated to the eigenvalue 4. Okay, so that's why there's a 4 here. So I know that that's what the answer will be when I compute P inverse AP, but let's just do it here. Okay, so P inverse AP. So 1/2 minus 1/2, 1/2, 1/2. That's my P inverse. Here's my A, 1 minus 3 minus 3, 1. There's my P, 1 minus 1, 1, 1. Good. So let's do the latter two multiplications first. So let me just write out the P inverse. I'll do that one later. All right, now if we multiply the second two matrices, it's easy to see we get -2, -2, -4, and 4. Okay, so check that. So that's the product of these two matrices I just wrote down. And now I'll do the product of those two matrices. So let's just do it in our heads here. So top row times the first column is going to be -1 plus -1 gives me -2. So far, so good. What's this? The entry in the bottom of the first column? Well, that's going to be, looks like 1 minus 1, a 0. Okay, that's good. What about the top right corner? So first row of the matrix on the left times the second column gives me -2 plus 2, gives me 0. Good. And the bottom right entry will be the second row dotted with the second column of those two matrices. So it looks like it's going to be 2 plus 2. Good. So it corroborates our calculation. I didn't need to do that. This is just a verification. So this is a verification. It's not, you don't have to do this to find D, you know, is just verification. And what I mean by that is we know D is this, okay? We know that already. That's from the theorem, okay? But this is good just to check your algebra, see if everything's working properly. All right, so let's move on. Good, so this is what we mentioned above. The discrete eigenvectors, they're orthogonal. When we normalize these, we get an orthogonal matrix. Good. So the matrix we're going to form now is going to be an orthogonal matrix. Okay, so recall for orthogonal matrix, P P inverse is the transpose. Okay, so that's the reason there's a P inverse, a PT here on the left, where before we saw the P inverse. That is the P inverse, all right? But we write it this way because it's orthogonal. You could still write P minus 1. You can do that. But because orthogonal matrices have that remarkable property that the transpose is its inverse, we tend to write PT whenever we are writing the inverse of an orthogonal matrix. Okay, so that's the difference in the formula. It's the same formula except we're using the transpose to denote the inverse. Okay, so it's slightly different than in the case where we don't have an orthogonal matrix P, which is true in generally if A is not symmetric. Okay, the P won't be orthogonal. Okay, so let's go on. So now I'm going to do the same kind of problem here. Okay, so this was, as it's stated in the notes here, this is the method of section 6.2. Okay, so the method of section 6.2 was just diagonalize a matrix. So go through this algorithm where you have to extract a basis of eigenvectors, form the matrix P in the way that I described here, right? P's got to be the matrix with columns of eigenvectors. Then this diagonal matrix that's similar to A will be the diagonal matrix with entries, the eigenvalues. So that is the method of section 6.2. The method of this section, 8.1, all right, so orthogonally diagonalize. Notice there's another word here, orthogonally diagonalize. Last time we just diagonalized the matrix. Now we're orthogonally diagonalizing the matrix. So here, let me just, why is there this extra word here? i.e., P will be an orthogonal matrix. So that's the nomenclature. That's the lingo we use when we talk about diagonalizing a matrix. When we say orthogonally diagonalize, the word orthogonal there is referring to the matrix P. Okay, P will be orthogonal versus just plain old diagonalizing a matrix, which does not guarantee that the P is orthogonal. Okay, it's just an invertible matrix. So this extra word is denoting that the P will be orthogonal. So we have quite a task in front of us, don't we? Because orthogonal matrices, if you recall that lecture, they're remarkable matrices. They have orthonormal columns and orthonormal rows. I mean, it's hard to come up with them. However, as we'll see here, when we diagonalize a symmetric matrix, we will be led to an orthogonal matrix P. That's one way to construct these orthogonal matrices. Okay, so let's see it happen here. It's not much more work. So we go through the same procedure here. All right. Actually, I should have just done this. I should have just extended this example, but we'll go through the same steps here. We'll extract eigenvectors, okay? Except when we form the matrix P, these eigenvectors you see in this example here, okay, there's the V2 and there's the V1. And there's my matrix P. Okay, so you can see that this P here. The columns are orthogonal and the rows are orthogonal. However, they're not orthonormal. Okay, so there's just a little bit more work to do. What we're going to do, and I'll do it in this next example, but let me just describe here. We have to normalize these eigenvectors. Okay, so we have to divide by their norm so that the norm of the new eigenvectors is 1. Then I'll form the matrix P, and its rows and columns will be orthonormal. Okay, so just one extra step. So that's why I'm not going to write all the details in this example down, because you know what I'm doing. So let's do this. So we first find eigenvalues. So we find the characteristic polynomial by computing that determinant. Okay, so lambda minus 5 minus 2 minus 2 lambda minus 2, and I compute lambda minus 5 lambda minus 2 plus 4, or that's going to be a minus 4 by this point, minus 4, and so we get, if I simplify that, lambda minus 1, lambda minus 6. All right, so it's a quadratic that I can easily factor. I'll just say that's equal. So let's call lambda 1 to be 1 and lambda 2 to be the eigenvalue 6. So I already know that my D matrix is going to look like this. If I order the first column of P corresponding to eigenvector from lambda 1, it's going to be 1 and then 6. All right, so I know what the D looks like. I don't have to do that long calculation. See, if all you wanted to know is what is the D that it's similar to, you just have to get the eigenvalues and then string them down the diagonal of this D and you're done. You don't have to compute the P, okay? But we often do want the P also. So let's continue. So that I know what the D is. And now let's get the eigenvectors. So we form these systems of equations. These are the coefficients. So there's my lambda 1, which is 1 minus B matrix. Okay, so it's this matrix minus 4 minus 2 minus 2 and then minus 1, and we will reduce that to this matrix 1 1 half 0 0, and from here I get V1 is, I'm going to extract so okay, let me do it in 2 steps so you don't get confused. So just reading off, calling the second variable the x2 variable the free variable, you'll see I'll get minus 1 half and 1. So I'll take my V1 to be a multiple of this vector minus 1 half and 1, and I'll just multiply it by 2 so I can get rid of that fraction. So minus 1, 2, okay. So that's a multiple of this vector minus 1 half 1 without fractions, okay. And then you can check that a V1 equals V1, okay. That's what you do along the road just to check your calculations. So the second eigenvector, there's only one eigenvector for eigenvalue 1, and we'll see there's one eigenvector for eigenvalue 6. So we do this, we solve this system, which looks like this. Okay, and I will reduce that matrix to this one, and then I'll read off V2, and I'll just read it straight off the matrix there. So I'll get 2 and 1. All right, so let me call that one my V2. Let me just rewrite it again here so they're all together. And then you can check that AV2 equals 6V2, okay, just to check. All right. Now, once again, observe that they're orthogonal, that V1 dot V2 is 0, okay, which was guaranteed by the theorem, which we didn't prove, that orthogonal matrices have or eigenvectors for different eigenvalues are orthogonal. Now that proof, you know, it's certainly within grasp of us, just like the proof of the statement that eigenvectors from different eigenvalues are linearly independent, the one I mentioned at the beginning. That's also within our grasp, both of these statements, and they're kind of similar. If you ever looked up the proofs, they're kind of similar. Okay, but anyways, that's not what we're going to pursue here. So we just observe that they're orthogonal. Okay, now to find the orthogonal matrix P, we normalize these vectors. So they're already orthogonal. Okay, so this is the extra step we're doing now that we did not do above and we did not pursue in section 6.2, and we're merely diagonalizing a matrix. We're orthogonally diagonalizing a matrix. So now we're doing this. So let me put that over here where we are orthogonally diagonalizing Okay, so this is where we're doing the orthogonalization, okay, if you want to put it that way. We normalize V1 and V2, okay? So let's do that. So my W1, let's call it, will be the, it's very easy to normalize a vector. It's going to be, you take uh, you take the vector v1 and you divide it by its norm. Okay, so in this case, it's 1 over root 5. All right, and remember v1 was that one up there, so it's going to be minus 1 over root 5, 2 over root 5. Okay, so there's that's the eigenvector I want from my eigenspace corresponding to lambda 1. All right, remember there's infinitely many eigenvectors. They're all multiples of this, in this case, this one up there, minus 1, 2. They're all multiples of that. So you extract the one that has length 1, the one that has the one that is normal, we say. So its length is 1, and you just divide it by its norm. So I did that. So my W1 now is the normalized eigenvector, and W2 will be my normalized eigenvector for the second eigenvector, V2, and V2 also has norm root 5, just turns out that way. Okay, so this normalized eigenvector will be 2 root 5 and 1 root 5. All right, so these are the eigenvectors you use to form the matrix P. In the previous case, I should mention here, in P up here, you can take any multiple of these eigenvectors, okay? So there's many P's, matrices. Their columns will be multiples of each other, okay? Of course, the corresponding columns. So you can choose any one of those vectors, v1, v2, or any multiple of those two, form the matrix P, and form this product P inverse A, P, that will always equal the same D, though, minus 2, 4. Okay, so there's a lot of flexibility here in the matrix P you want, even though the columns must be made up of eigenvectors. You can select any multiple of the eigenvector for the columns, okay? But that's not what we can do down here. Now we're selecting from all those possibilities of columns, we're selecting the eigenvector that has length 1. Okay, it's got to be that one. So now how does it look for us? So let's write down our orthogonal matrix P. Is going to be, so I've ordered my eigenvalues already, right? So the lambda 1 was eigenvalue 1, and that corresponds to this normalized eigenvector W1. So I have to put that one in my first column. There it is. And I'll put in my second column, I put the eigenvector corresponding to my second eigenvalue in my diagonal matrix, which is 6. And that's the W2. So 2 root 5, 1 root 5. Okay. And now I don't have to go compute the inverse, right? Because the inverse is the transpose. Because that is, look at it, that's an orthogonal matrix. Its rows and columns are orthonormal vectors. So the transpose is the inverse, and the transpose is this matrix here. That's the first column, and then the second column. Okay, so you can check that that's the inverse. So P PT equals I. Okay, you can check that. So now we write down, we're done. I mean, that's the orthogonal matrix that diagonalizes B. Okay, so maybe I'll just write that down because you hear this kind of lingo. P is the orthogonal matrix that diagonalizes B. I.e., what that means, that's an English sentence. What it means in mathematics is PT, B, P will be D. So let's just do that here. So minus 1 over root 5, 2 over root 5, 2 over root 5, 1 over root 5. So there's my PT. Here's my B, which was 5, 2, 2, 2. And then my P, which is minus 1 over root 5, 2 over root 5, 2 over root 5, 1 over root 5. And let me just do the second two matrices first. I'll do that multiplication. So this is the same matrix I see on the left, the PT, right? So 2 over root 5, 2 over root 5, 1 over root 5. And then when you do that multiplication of B times P, you will get minus 1 over root 5, 2 over root 5, 12 over root 5, 6 over root 5. And then finally, I'll do that multiplication, and then I'll see I get my diagonal matrix, as I should get, equals D. All right, so that's the meaning of that English statement. P is the orthogonal matrix that diagonalizes B. It means that when I write this combination, and it has to be this combination, so PT on the left, BP, I get it to be equal to D. Okay, good. So now the principal axes theorem, okay, which is actually this one right here. I'll just highlight it. Okay, there's a few statements on this page, but it's this one here. Principal axis statement. Okay, so let's get to that in a second. But first we have, just repeating some of the facts above. Once again, and look at that m by n. It looks like nxn. It should be n times n. Okay, but you know what we mean. So there's my nxn square matrix, symmetric. Eigenvalues are real. Okay, facts, as was mentioned above. Now, the second statement there is more general. Okay, it's an n by n matrix, but all we say it has, all we're saying is that, if I have a matrix that has all real eigenvalues, okay, so I should write some comments here. A not necessarily symmetric, okay, just an arbitrary one. But it is a special matrix in the sense that its eigenvalues are only real, okay. Okay, so maybe I'll add that here just to emphasize what the difference is between this statement and the more general one the more specific one we were talking about. So A not necessarily symmetric, but has only real eigenvalues. Okay, so no complex eigenvalues. Okay, so it is a special kind of matrix still, all right, but doesn't have to be symmetric. Symmetric are matrices like this, okay, but these don't have to be symmetric. If this matrix has only real eigenvalues, it's orthogonally similar to something, okay, but not a diagonal matrix necessarily, an upper triangular matrix T. So it's orthogonally similar to a triangular matrix, not necessarily orthogonally similar to a diagonal matrix. So what it means is the following, that there's a orthogonal matrix, and I'll denote it by P again. So when I write out this expression again, so PTAP, what I get is this triangular matrix T. Okay, now T, remember, upper triangular matrix. So let me just say a comment here first before I fill out what this T is. A is similar to T. Remember that. We talked about similarity. A and T have the same eigenvalues, okay? So that's a fact from back there, some chapters back, eigenvalues, right? Remember that? Similar matrices have same eigenvalues. So I'm going to write out. Now, the second fact is, I'll put it here, the eigenvalues of a triangular matrix. Remember, a triangular matrix, upper or lower, and diagonal is one of those too. Okay, diagonal is actually either one. So for all these types of matrices, triangular matrices, eigenvalues of triangular matrix are the diagonal entries. Okay, remember that? That's very important. Easy to see. Just do the calculation. Okay, expand across the first row. Okay, keep expanding across the first rows of all the minors. Then you'll get that answer. I don't need a bracket. Okay. so I'm stringing this together because I'm gonna actually write out what this a little bit more what this triangular matrix looks like. So T and A have the same eigenvalue. So I'm going to write the diagonal entries of this triangular matrix as the lambdas. Now, all real eigenvalues. Okay, so there they are. Now they don't have to be distinct. I'm just writing them all out. And it's upper triangular, so it's zeros down here, and then it's stuff up here. Okay, so the stars just mean possibly non-zero entries. So I'll just put it up here. Possibly non-zero entries. Okay, but zero below the diagonal. That's an upper triangular matrix. So that's what this statement is saying here. What else do I want to say here? Okay, that's enough, right? So that's illustrating what a matrix that has only real eigenvalues is similar to. Okay, upper triangular matrix. So no proof here. Okay. But that is something that is used often in applications. The next statement, the principal axis theorem. Notice it's an if and only if statement. Okay, so you have these two statements here. Okay, so you have asymmetric implies orthogonally diagonalizable. Okay, and then we have the converse. So if A is orthogonally diagonalizable, then it must be symmetric. Okay, so that's what that principal axis is saying. Let me just remind you this English sentence again, orthogonally diagonalizable. So that's a sentence we can and will use on an exam. You have to unpack it. Here it is. It means that, didn't I write that down somewhere up here? Yeah, maybe I'll put it right here. Okay. Or maybe I should just put it back here. Okay. It means that there is an orthogonal matrix such that PTA P equals D. Okay, so that's what that sentence, A is orthogonally diagonalizable. It means that. It means this mathematical equation with these three matrices. Okay, so remember that. Asymmetric. Okay, so this principle, before I say something about why they call it the principal axis, whatever that is, okay? Where's my pens? They're there. There's these two statements. So there's this one implication, and then there's this second one. Now, it's the one that we're usually pursuing. Okay, we're usually trying to find this orthogonal matrix P, and then at the same time what the D is. Okay, the eigenvalues would be forming the matrix D. So that's usually what we're doing. 2 is not usually what we're doing. I mean, I'm not going to orthogonally diagonalize the matrix and then just to prove that it's symmetric. I'll simply look at the matrix and see if it's symmetric. Okay. Nevertheless, there might be situations where, in some abstract sense, you know that this matrix is orthogonally diagonalizable, even if you don't see it. But for some reason you know it, then you can surmise that it actually is a symmetric matrix. Okay. However, it's the first statement. The first implication is what we will usually be pursuing, and actually this is the one right here, right? I'm pursuing that one right here. I have a symmetric matrix. Okay, I'm going to orthogonally diagonalize it. Now, I know it's orthogonally diagonalizable. That's what the axis theorem says. I'm going to find the matrix P and the matrix D. So now, principal axes. That's interesting. This comes from geometry, from quadratic forms. So forms, conic sections, quadratic surfaces, in R3, conic sections in R2, conic sections, hyperbolas, ellipses, and similar things in 3 dimensions. That's what it's referring to. So if you recall your, I'll just make a little sketch here. So here's an ellipse in 2 dimensions. These are the principal axes right here. The one that goes through the longest direction and the shortest direction. These are the principal axes of that shape. And they're associated, they are the eigenvectors of a symmetric matrix that is attached to the equation for that ellipse. Okay, so eigenvectors of a symmetric matrix. So I'm not telling you the whole story. It's a nice story. There's some mention of this in the textbook, how this works. And if we had more time, this would be something I would pursue. But that's the origin of this term, principal axes, associated to this symmetric matrix, okay? To resolve any mystery that you might have about it. All right, so let's do this task. Now I'm doing the longer task, and I know time is really going fast, eh? So I'm going to do this one quickly, and you can verify some of the calculations. So the task, like this could be a test question, okay? Orthogonally diagonalize this matrix. Well, you roll up your sleeves and you go through this whole process that began in section 6.2 about diagonalizing a matrix. You go through that whole process, eigenvalues, eigenvectors, but to orthogonally diagonalize, right, there's this extra step you do at the end, and you orthonormalize the eigenvectors. Okay, so let's go through here. So first, maybe I should write it out this way: eigenvalues. All right, this is always your first step. So eigenvalues. So you go the determinant of lambda I minus b. Okay, so you're gonna have lambda minus 1, 0, 1, 0, lambda minus 1, minus 1, 1, minus 1, lambda minus 2. Okay, compute that determinant. Okay, so I'll expand across the top row, and I'll get something like this. You guys can verify lambda minus 1, lambda squared minus 3 lambda plus 1 minus lambda plus 1. And finally, I'll get this to factor into 3 terms. All right, so this is a cubic. It's a 3 by 3 matrix. So the characteristic polynomial will be a cubic. And that might send shudders down your spine. Okay, I got to find roots of a cubic. Well, I mean, for tests and stuff, we'll make them pretty predictable. So you guess a root. And so here's 0. I mean, you can see in this particular case, it's easy because this quadratic or cubic, if you write it out, it has no constant term. So 0 is a root. So you factor out a lambda, then the rest is a quadratic, and you use quadratic formula if you want. Okay, so it's usually a guess at a root on a cubic, and then a quadratic formula for the other part of it. So anyways, that's what it is. And so I see my eigenvalue. So let's choose an ordering, lambda 1 to be 0, lambda 2 to be 3. So this ordering, remember, is going to appear in the diagonal matrix. So I'm going to just write it out here. My diagonal matrix is going to look like this. I know that much. If that's all I wanted, I would be done, okay? But that's not diagonalizing, or that's not diagonalizing a matrix. That's just finding the matrix that it's similar to, the diagonal matrix that it's similar to. This is all you would have to do. All right, but I need that. I need the P now. So to find P, you need eigenvectors. Okay, so here we go. All right. So luckily, I just have to write them down. You guys can verify. Um, I should say normalized, okay? Because I want an orthogonal matrix P, okay? So normalized. So you'll have to do this. You find the eigenvectors first, and then you extract the multiple that has norm 1, right? So you take the particular eigenvector that has norm 1. And that's been done here. So you can check that these all have norm 1. And if you don't believe me, you can check that. What are we calling it? B? Yeah. B V1 should equal what? 0 times V1. Yeah, so it equals 0. Good. This is just a check, right? So not necessary if you're in a rush. V2 is minus 1 over root 6, 1 over root 6, 2 over root 6. All right. So you can also check that B acting on V2 gives me 3 times V2. Okay. So that's the eigenvector for eigenvalue lambda 2, which is 3. And V3, you guys don't mind. Sometimes I put arrows on my vectors, sometimes I don't. That's not necessary. You know what I'm talking about. Okay. So V3 is 1 over root 2, 1 over 2, 1 over 2, it looks like. Okay. And then a 0. Okay. So just to confirm, no mistakes in algebra, this will be just V3. So this is the eigenvalue 1. Okay. So these are normalized, right? So I'll highlight that because you can't form an orthogonal matrix out of vectors that are not orthonormal. Okay, orthogonal. If you use just orthogonal vectors, so the vectors you would get initially when you find the eigenvectors from the eigenspaces, they will be orthogonal amongst each other. You can check these are orthogonal, but these are the normalized versions. If you just selected orthogonal vectors and you formed a matrix P, it would not be an orthogonal matrix, right? You took orthogonal vectors, it would not form an orthogonal matrix. You need orthonormal vectors to form an orthogonal matrix. So that's why we normalize them. And now I'm going to form my matrix P with these orthonormal vectors as columns. So there it is. Okay, so now I'm going to put them in the same order as I have my eigenvalues here. Okay, so that first column of P corresponds to the first eigenvalue in the top corner, lambda 1, which was the 0 eigenvalue, so that's V1. And then the next entry, the second column, has to be the second eigenvalue as you go down the diagonal, and that was eigenvalue 3, which was my lambda 2, and my eigenvector, normalized eigenvector, was V2. So that's minus 1 over root 6, 1 over root 6, 2 over root 6, and then finally 1 root 2, 1 root 2, 0. Good. And there's my D. Okay. So now show, or I should just say verify for yourself. Okay. So verify that when you do this PT times B times P, you do get D. Okay. So I want to go back to what I mentioned at the beginning. So a note here. Here, each eigenspace is one-dimensional. Okay. Okay. If an eigenspace, so I'm talking about some other situation, let's say EK of symmetric matrix. This one was called B, right? So let's just say A now. Is say dimension what letter should I use? M, bigger than 1. Okay. So in other words, there's when you solve initially, you obtain a basis for EK right? So like my notation above, BK would be, so U1 up to UM, right? Via solution, right? You'd have the x's, you'd have these free parameters, and you'd identify those vectors like that. Remember that? At the top I said that. Okay, so when you look for the eigenvectors of a matrix, you solve that homogeneous system. Once it's solved, you write out the solution set this way, don't you? You identify your free parameters. Then you extract from that vector equation the basis vectors u1 to um. Okay, now they're just linearly independent. They won't typically be orthogonal. So here's the extra work you have to do in that situation for orthogonal diagonalization. So now apply Gram-Schmidt method. I hope I'm writing this properly. Probably not the spelling. Gram-Schmidt method to bases BK to obtain an orthonormal basis. Okay, let me call it BK with a tilde. Okay, so these would be, they don't have to look anything at all like the U's. Okay, so W1, but there'll be M of them. All right, so I did Gram-Schmidt to the bases BK, which are the vectors U1 to UM, which are merely linearly independent eigenvectors corresponding to the eigenvalue lambda k, I guess. I applied Gram-Schmidt, which was a discussion in chapter 7, I think, where I obtained from that an orthonormal basis for the eigenspace. Okay, so this BK tilde is a basis for EK. Now use vectors, these vectors, W1, Wm to form P. All right, so that's even more work in the situation of orthogonal diagonalization to form P. Let me finish this. Okay, so when you diagonalize a matrix, you find eigenvalues and then all the eigenvectors, and then you form the matrix P that diagonalizes, and then you're done. If you orthogonally diagonalize, you have to do another step. You have to make sure your eigenvectors are orthonormal. In this previous example here, this 3x3 case, the three eigenspaces were one-dimensional, so I didn't have to do any work. Okay, I didn't have to do the Gram-Schmidt method. But if one of them was 2 dimensions, okay, if one of the eigenspaces here was 2-dimensional, then I'd have 2 vectors in that eigenspace, 2 linearly independent vectors as a basis. I'd have to make them orthonormal by applying the Gram-Schmidt method, which wouldn't take long in that case. But remember, Gram-Schmidt method means you start with the first vector, you normalize it, then to get the second vector, you pull out the second vector in your linearly independent set, and you remove from it its projection along the first vector. Okay, remember that? That's what you were doing. Then that remaining vector is orthogonal to the first one, and then you normalize it. So Gram-Schmidt first finds orthogonal vectors, and then you normalize them, and you get an orthonormal set of vectors. Okay, so you'd have to do that extra work with the Gram-Schmidt method, and typically that's what you do because eigenspaces typically are bigger than 1 dimension. Okay, so you will typically need to do this Gram-Schmidt method on every eigenspace that has dimension bigger than 1. You have to do that. Then you form your matrix P from those orthonormal bases, okay, from those orthonormal bases. So that's the work that you have to do. And that's it for today, folks. So I think I'm done, and we'll see you again another time.